I was trying to, I feel very strongly that Grassmann's, also mix up the G-men, Galileo, Grassmann wrote, Grassmann's idea about equality and difference is certainly very intimately related. If we want to make a precise one-to-one correspondence, or something close, then there's a struggle, to make that as clear as possible. So the nearly equal, the infinitesimals identified as the nearly equal, identified as the spaces where the pieces every piece has a unique point, and so forth and so on, seems to be a good start. What about the idea of the difference? Things being different. Well, I think, it means many things, obviously, but one sort of thing that it means is apples are different from pears. Now, you can have a lot of apples, which in one sense are different from each other, and a lot of pears, which in one sense are different. You know what are pears, right? I didn't say pears, but apples are different from pears. So, in other words, I was just thinking this morning, maybe this doesn't really make sense, but I wanted to say that the map is different. If when you go down to the components of the codomain, the pieces viewed as a space in its own right, the composite is a monomorphism. This loop means it's a monomorphism. Well, we always have this problem with grammar, you see, when we talk about general concepts, but it is different, or X are different, you wouldn't quite want to say, but the idea is that the points in A are, this may be a bunch of fruit, you see, and you're mapping it into kinds of fruit, and you want them to be still. So it means, for example, to say that two global elements, are different, says that they actually belong to different components. So I'm saying that the idea that 2 points can be not only naively different, but actually belong to different components, that is a reinforced form of difference. I was relaxing the idea of equality to have almost equal. By contrast, I'm strengthening the idea of difference to mean really completely different, i.e. different components. Well, so anyway, this is connected with another construction of extensive quality. Grassmann correlated different with extensive, and intensive with equal. So the infinitesimals, obviously, there's something intensive about them. That seems rather intuitive. What about extensive? Well, there's another quality, or in some cases, here's an attempt, a very important attempt to construct another quality due to Hurewicz. There's a Hurewicz category associated to a given category E. And what that is the objects are the same, the spaces in E, but it's actually a U enriched category. It's not just an abstract category. It's enriched over the same base that we had before. So the space of points of the maps between two things is the components of the function space. I'm assuming that the category E is Cartesian closed, but we also have this functor P lower shriek. Remember the usual, what we sort of intuitively think of as the arrows from X to Y, that's the set P lower star of the same function space. This should be a relatively familiar idea, but we can, instead of P lower star, we can apply P lower shriek, and we get a completely different U-enriched category. I call it her A-rich category. Now, why is it a category? You have to. This is one of the several places where the fact that P lower shriek preserves products comes in, because you need composition for a category. Given any three objects, any three spaces, x, y, and z, you need to compose the elements of this so-called set of this Hom set. So this composition is defined starting from the strong composition that you always have in any Cartesian closed category. Whenever you have a Cartesian closed category, there's a canonical thing like that. So you apply the P lower shriek functor to this diagram, but you have to be able to commute it with the cross in order to arrive at that, right?
Can you push it?
Oh, sorry. No, sorry. I don't know, this seems to be the sort of thing that people working in lambda calculus never thought of. I don't know, it's obviously directly relevant to lambda calculus because, by the way, see this Hurewitz category is again Cartesian closed. In fact, in a very, very nice sense, because the sums, products, and exponentials are the same ones that they were before. The same objects that the actual function space, the actual Cartesian product, and E, those objects still satisfy the same adjunction after you change this. This is a general feature about enriched categories and closed categories, but applied in particular in the Cartesian situation. This is again Cartesian closed. Again, a model of lambda calculus, in which if you have this P lower shriek operator, one model of lambda type lambda calculus, or even non-type calculus. Now the thing is that this is again, okay, I need another sheet. This functor little h, it's just the identity of objects, but it's the map from on each Hom set. It's just a map from points, which is E of x comma y, whatever you want to call it. In other words, a standard map from star to shriek, but applied in particular to an exponential object. It tells you how to map the Hom objects here. So this little h is called the homotopy type. So every space has its homotopy type, which is an object in this presumably simpler category. It's not that much simpler. But now, technically, if E, I usually want E to be a topo, actually. I'm only so far, I've mentioned the third axiom for cohesion, very much tied up with the value of the partial map classifier. But most of the construction just depends on Cartesian closure and extensivity. Extensivity and Cartesian closure are two distinct reasons why you have the distributive law of sums and products. Extensivity implies a distributive law. Cartesian closure implies a distributive law, but neither one of those implies the other. They're sort of two. Hiding algebra is Cartesian closed but not extensive. In countable sets, it's extensive but not Cartesian closed. There's sort of two different reasons for fundamental distributivity. But, so, the thing is this, so there's an obvious functor here, which is just, again, represented by 1. For Hurewitz category, the maps from 1 into something, well, that's a U-valued functor, of course. But notice what it is, it's actually the components of X. So what to this category seem to be the bare points, or the points, is what were the components, pieces originally. So you've taken these objects and you've defined new objects whose points were the old pieces. But it consists of much more than just points, because the figures of various shapes also survive. And of course, the idea in homotopy theory was the crucial kind of figure is a sphere. A sphere, not a ball, a sphere. The surface of the circle, two-dimensional sphere, which is the surface of three-dimensional ball, etc. That the meaning of the maps from each particular sphere into a given space Y, taken all together, somehow are a system of very profound invariants of the space, which come up in all kinds of analysis. Now, what I wanted to say was that this ought to be equality. You want homotopy to be equality. But you need a little bit more. You need that the components of x to the power s should equal components of x to the power s, where s and u. See, my axiom 1, the thing that was needed to define this category at all, implies in particular that this is true if x is finite. If s is finite. P lower street preserves products, finite products, and so on. But, and finite is typically coming from U itself. It's a discrete thing, relatively discrete thing. But a stronger condition, actually I took it as an additional axiom in the paper that's in the tag. This is needed in order to imply that this is equality. That is to say that the left and right adjoints are the same. Or you don't know what the other adjoint is. The only one you know about is taking the component. But that same functor which is manifestly one kind of adjoint, should also serve as the other kind of adjoint. That's the condition that I want to say, to make it equality type. And that's equivalent to this additional sort of continuity condition on the act of taking components. Now, what does this mean? This is false for the usual combinatorial models, the simplicial sets, cubical sets, and so on. It isn't quite true. And that's what really gave rise to the whole industry of equivalent models and so forth, because you have to identify objects a little bit more than they're getting identified by. Of course, many arrows in E are going to become isomorphisms here, because if you have reversed arrows, two arrows back and forth, such that the composites are not necessarily the identity, but just in the same component as the identity, then they will be inverse after you collapse into here. After you go here, they become inverse. Those are what's called classical homotopy equivalences, and there are loads of those. But you need weaker equivalences in order to get, you get stronger properties required, of which this is just a little fragment, which interests me. Now, on the other hand, it is true in continuous cases, that where you deal with actual continuous spaces, not just combinatorial models for them. And it's also obviously true in what I think is an important class of things, namely toposes where the Hom sets are finite graphs, finite dynamical systems, finite autonomy, finite permutations, representations, and finite groups, finite monoids. There's a vast amount of mathematical information in that particular two category. And there, but very few people have actually looked at the homotopical aspect, the variance of graphs, for example. just the homotopy category of reflexive graphs is still quite complicated. In fact, I think it's equivalent to the usual homotopy category of all topologies of CW complexes. I think that's right. So, but if the Hom sets are finite, then this is true just because S is finite, and we already hypothesized that in the first axiom. So we'll get a quality type, and a particular quality H, whose values are in that type of quality, associated to every finite automaton, every finite coset, etc. And it will satisfy its property of being a quality type, as well as what it always does is to preserve. It gives another model of lambda calculus, if you want to look at it that way. So if this is true, whether it's because of continuity, or because of finiteness, or because I force it to be true by a further Quillen construction, which actually originated in the book of Gabriel and Ziesmann, known as Categories of Fractions in Homotopy Theory. So there's three different ways in which this might be true. But it's equivalent to the fact that this is a quality type. But it's an extensive quality type. Because H is compatible with the components aspect. I didn't give this a name, but what shall I call it? Well, it's the components. Well, let's just call it P bar. This was P, that's P bar. So clearly by construction, P bar H is equal to P in some sense, but in particular, it's for the shrieks. P bar lower shriek, which is the same as P bar lower star, that's what it means to be equality, but that's going to be the same as the components of the original space, the general space. In other words, what we're doing is souping up the space of components. We're saying that space of components is not just an abstract set, it's a whole homotopy type. And so it's extensive because my definition of extensive is compatibility with the left adjoint. Whereas extensive for a quality type, whereas intensive for a quality type was compatibility with the right adjoint, the points. And this, see again, intuitively, I don't know exactly to express this in exactly what, but the homotopy, the idea that in the homotopy category, for example, if you have two maps, they're different, they're really, really different, because it means there's no way to even continuously deform one into the other. In the original space, E, we deform maps into each other. They'd be in the same component of the function space. But after you've passed to the homotopy category, two things are really, really different. So in that sense, we can force it. And we somehow managed to, by twisting words in the most unprincipled manner, we've been able to make a reasonable correlation between extensive and different. So, and actually notice that there are two. This is an important extensive quality. Homotopy type is certainly an important. But there's another one which is valued in the same L. As if we take the substance, going back, remember the substance, the Bose aspect of the substance, rather than the Avogadro aspect, the Q, the construction that we made before. Well, this one, of course, is now an extensive quality type also. So this is another extensive quality type because it's compatible with the components. Now, the Bose picture had the same components as the original space. It just identified all the points so that the whole component became, there's only one nucleus, so to speak, but it's still has almost all the same stuff. It's a collapsing to, it's got the same compatibility with P lower shriek. Q lower shriek, or S lower shriek, of course, as P equals QS, and you take the left adjoint, so the adjoints compose here in Tom's paper published 50 years ago, adjoints compose. And of course, but on the other end, Q lower star is really the same as Q lower shriek because this is quality type. So, and this one has a topos as values. I didn't prove that, but typically the L is also a topos, unlike the Hurewicz. So an extensive quality type, an extensive quality whose type is not only a quality but even a topos. By the way, they should have said something more about that. If you take the monoid generated by a single idempotent, or inside S, where S is any given topos, this is a quality type. This is a simple example. If you have a space in which idempotent acts, then the fixed point of that idempotent extracts points, but those are also the components, because everything. Chanuel had this picture about this particular thing. You have all the peasants belong to some castle. So when enemies threaten, then all the peasants run into the castle. A lot of dots, and they all go into some particular main dot, and the main dots are the ones that are fixed. But you can think of it either way. It's an equivalence class, where it's the main point. Duke is the main guy. There's a one-to-one correspondence between dukes and chieftains. That's one of many ways to think of this. And of course, this is literally the L which arose for the reflexive graphs. In other words, if I start off with the idea of graph, pretty complicated, and I come to the simple idea of, graph where everything is a loop. But the latter thing is really equivalent just to a single map that's split. Because source and target are equal. So it's really just a set with one input. You draw it differently. You think of the general element as a loop, and then the fixed point is the actual dot. You can just think of it all the edges is one set, have to be loops. Among those are the degenerate loops, and to every loop you attach the degenerate loop that lives at that loops are degenerate loops. So that's the most general quality is of course more general than that, but the example that we have, it does reduce to the same construction. Essential quality. How do we construct examples? Well, I'm always the axiomatic method, or some computer scientists who were interested in synthetic domain theory or something. They asked me a couple years ago, what does synthetic really mean? Well, I'm not an expert in where it came from, but what it means for geometry, sine and so on, is that you start like Hegel says you should start. In other words, you start with the whole thing is already given. You don't know anything about it except that it's given and it has a certain name, which implies something. You don't start by building it up out of nothing into space. You say, it's here, and well, look at it. It has these properties. It has all these interactions. Ultimately, I might be able to build it up. It's like the notion of, as I said, graph mining. Graph miner should not be something that you just build up. You should also know where you're going in a general way. Then you find out through years of work where you're going in a particular way. To know where you're going in a general way is what you should start with, not end up with as a row. So it just occurred to me to put Hegel's name there, because that's the kind of thing you do. So if you imagine, I'm in a category of spaces, you start with that. What could that possibly mean? And you look at it more and more closely. And maybe you can analyze it. Well, the way that we always think of building up Rotary topos, for example, is, well, you start with set, and then you have a site, and so on. But actually, Cantor tried it another way. He said from Mengen, see, I'm freely interpreting that Cantor was really a precursor to category theory. Because you said, well, there are these Mengen, pretty complicated. But notice in particular, I've got this brilliant idea. We can extract from a Mengen, we can extract just some bare dots. He calls them lauter Einsen auf Deutsch. Lauter Einsen. We can extract that. Then we'll have this amazing property that the points in the plane and the line become the same, because the abstract thing that we extract from them, I can show are isomorphic. Using an idea I learned from Steiner, by the way. He says I learned from Steiner. Anyway. So, and then he calls them his old cardinalin, by the way, which is not after the equivalence classes. He knows about the equivalence isomorphism classes, yes, but the cardinalin are, as I understand it, not they're what you get by. So this is but this is kind of a double negation. And I'm saying that Cantor negated this vague idea of Mengen by saying, let's look at things that have no cohesion. I mean, the Mengen are things that have cohesion and variation. We study in mathematics all kinds of things that have cohesion and variation. You negate that, we come to the abstract sets. The double negation is, we can actually use the abstract sets as a basis for modeling all kinds of things. So let's see what that means. So we start with E, the Mengen. It's a version. So I'm saying the double negation involves the idea that Mengen come in many categories. As I said at the beginning, you need, with Maxwell, to screw up or down the precision, or use the maximum technology you need, or the minimum technology you need. That's a variable. So there's not just one category of Mengen. No, all of the cohesive topos should be thought of as different levels or different. Okay. So, but anyway, we start with one. We start with the cohesive topos. E is a topos satisfying my axioms, for example. Although from what I'm saying, it can be much more general. Now, we want to find within that some spaces that are devoid of cohesion and variation. Imagine that the original objects have some specific category E. Again, the word category is some kind of cohesion and variation. But among those, there ought to be the ones that are relatively trivial, qualitatively trivial. Oh, I forgot to say one thing. I forgot to say one thing about my third axiom. Everything can be embedded in a connected thing. That implies that the cohesive topos is very much not the U that underlies it. Because here, the truth value object is getting killed off. This is not an isomorphism. It's very qualitatively different from an isomorphism. Or we couldn't, or the whole thing collapses. Everything can be totally trivial. But if it's not trivial, although it's not trivial, then it's very different. Very, very different. So it's not just some arbitrary subcategory we're looking for. It's something like that. So, and then, yeah. Let's start over. Yeah. The idea that mathematical objects are structures, and that's what I already said. No, they're objects in the category, but they can be represented as structures. Represented usually means something of the following sort, but in order to do that, we have to find two parts of E. The discrete part and the connected part, but defined by this orthogonality relation. Given any two objects in a Cartesian closed category, we can look at the function space S to the power D, and there's a canonical map from S to that. If you like, it's induced by the map from D to 1 in the exponent. But these are the names of maps, and among those there are always the names of the constant maps. So this equation is saying all maps are constant. All maps from D to S are constant. So this simple idea, from which it's easy to see, for example, that if you take such an S to any power x, then it still satisfies the relation with respect to the same d's, because this is S to the D to the x, but S to the D is S to the x. Just like algebra this time, exponential rules. Given a D, the S's are closed under raising to any power, any x. Similarly, for example, the S's must be closed under products, because if the S's, two S's are orthogonal to the same D, then since this is S1 to the D times S2 to the D, and that's S1 times S2. And so on. So there are certain closure properties automatically if you have two classes that are orthogonal in this sense. And if you have two, that for everything in this class and everything in that class, you have this relation. Now, typically this is known as a Galois connection. A Galois connection can be generated by a few objects on either side. So for example, if you suppose, as we were doing before, that U is given, you can define D to consist of all the D's to satisfy this with respect to all the S's of U. And those you might want to call, let's say, D connected. So are U connected? The idea is, of course, that somehow, if you want to parameterize motion by D, then the only motions that are in S are trivial. You can't get anywhere, because D is so discrete. Or because D is so connected. Those are sort of dual reasons. I guess this is a familiar idea, I don't know. But on the other hand, if you start with some objects in D, just some objects, then you can define the U to consist of all things, all the S's that satisfy this in D, and then define script D to consist of all the D's that satisfy this with respect to all the S's. A well-known game with Galois connections arising from arbitrary binary relation. Take this as your binary relation. Now, the thing is that for algebraic geometry, analytic geometry, smooth geometry, and many other examples, this whole thing is generated by one object, T, namely the infinitesimal space of 1 point and 1 degree of infinitesimal variation. So it's like Heraclitus is trying to move in one direction. There's just one object D. which is like, well, it comes from Heraclitus, from Hegel, from everybody. In other words, just the idea that in the real world, there's something called motion going on. Motion means to be in one place at one time, but not only in one place. So we import from reality, rather than constructing by starting at the empty set and applying mental things, we have this concept. There's still a total distillation of the idea of motion. We import that from reality and say it must be in our local scheme. It's an object. Then, of course, the problem is to find out all the properties that you have, starting from this point of view. But in particular, we can use that one object P to define a notion of discrete. And if you like, you could call it infinitesimal discrete. When you're thinking of D is infinitesimal. It turns out, by the way, that such a U defined that way, again, going back to the general class D, no matter what, you'll always have the P lower street preserving products, because, I think I mentioned this before, it's a general property of full inclusions, that if the subcategory is closed under exponentiation by arbitrary objects, then the left adjoint preserves products. So I don't just get a category U closed under various properties. In particular, I get a component, a pieces function that preserves finite products, which I need for all sort of. So that axiom is proved automatically. And even that doesn't depend on D being small in any sense, just that it's a single object. Now, there is this whole story, I don't have time, about D being an atom. There's a further property, say the silvery interpreted adjoint and so forth, which happens to be true in those three great infinitesimal theories, differential, algebraic, and analytic, which implies more property. It implies that there are further adjoints and so forth. Don't have time to. So, I think of, in some sense, the P lower street, the left adjoint, which does sort of automatically exist in the sense that after all the S's are closed under arbitrary limits here. The same calculation goes as well for arbitrary, because this is the right adjoint. So modulo is some usual assumptions. The inclusion has a left adjoint, called P lower street, called the fourth, called the components. And there's a thing by construction, because the view is defined in this way, that reflection automatically preserves finite products. In some sense, the first thing you come to is the inclusion of these S's and the left adjoint, which I sometimes I think of as counting trees. It's another way to think of these things. That if your object X is a forest, you want to analyze the wood in it. You might take as a first step just to count the trees. In general counting, I want to count people here. I don't count, human flesh. I count the components of human flesh. That's too personal. But I mean, right? You count, when you talk about counting things, you're treating the things as points. Same sort of thing Cantor wanted to do with the left adjoint. So you're treating the things as points, even though what they actually is called components with respect to something. If you count them with respect to nuclear physics technology, you'll get more pieces than if you count them with respect to classical chemistry technology. It depends on the topos you're in.
Listen here for a second. Just to give you, we have more or less 10 minutes more. Start an application. We have to leave the building at a certain point, so on.
Oh, yeah.
So, can you maybe a bit more.
Well, anyway, look, this is just an indication of how you can analyze this thing further. You can analyze E then as consisting of functors from D into U by the way of looking at the Hom objects. Arbitrary objects in E have Hom objects, which are then pushed down into U points functor. That's the usual point of view. So if you choose a subcategory of E sub 0, which can be quite small, which is sufficiently large, then by the standard method, you get a full representation of E. And so to be a space then becomes a property. This is a kind of structure, you're limited as a kind of property, and so now you reconstruct it. You see how it is. I'm back to the model reconstructed as a property of the structure, and the structure is determined by the D0. And if the D is an atom, in the sense that exponentiation has included the right adjoint, then all sorts of properties of differential calculus come out, as is perhaps better known from Koch's book and so forth. It just had a second edition, by the way, that everybody should buy and read. But a lot of it, so for example, yes. I want to say one other thing. That is, you see that the L is a quotient topos. L is a quotient topos. The infinitesimal objects. It's a subcategory. The objects where performance and performance have equal numbers, every component at a unique point. Those objects are a subcategory, but not a subtopos. It's a subcategory as the inverse image of the geometrical morphism, which extracts the Avogadro part of any object. That's what's it's actually a quotient topos. But quotients and subtoposes are really both part of a more general thing, which is lex idempotens. That's why in the notes I had advertised a particular paper of Paré, Rosebrook, and Wood. The left exact idempotents, you can split them. You can split them so one part is adjoint, and you've got a subtopos. You split them so that the other part is adjoint. You have a quotient topos. And in fact, the general one can be split in two steps, so that there's a one-to-one correspondence between left exact idempotent endofunctors of the topos and subquotients, subs of quotients. Also within that world of in fact, when you think of a subcategory of the topos, you have to see, well, is it a subtopos? It might be a quotient topos, it might be a subtopos. It's still described by a subcategory. And which of the functors is relevant? But so in particular, the thing which happens is that, for example, from a quotient topos, you can extract a subtopos, namely the smallest subtopos, which as a category contains the inverse image of the quotient. And this might even generate everything. So concretely, what we have is that there are often these cohesive topos are what I call infinitesimally generated. Because the category of infinitesimals, the L, or components equals points, as a subcategory, it's a quotient, but it's a subcategory going back, and the smallest topos that contains that is everything. Generates the whole thing. The whole thing is infinitesimally generated in that sense. See, concretely, a subtopos is always closed under this business of arbitrary exponents. On the other hand, it contains now the infinitesimal object. So you can exponentiate the infinitesimal object always within the subtopos that's generated by the given quotient. You can always exponentiate. But according to Euler, another one of the things that Euler said that wasn't nonsense after all, is that the real line consists of ratios of the infinitesimal. These ratios form the exponential. As soon as you have the real line, you have products of it, you have varieties defined in it, and so forth. You have the whole range of multidimensional geometry, infinite dimensional analysis based on particular infinitesimal object. All of that is inescapably contained even in the smallest topos that contains this quotient topos as a subcategory. And so that's what I mean by infinitesimal generation. And it surprisingly often holds. As the many open problems mentioned above strongly indicate, there are still a great many problems in topos theory and even in pure category theory that are, on the one hand, of a very elementary nature, and yet whose clarification still needs to be carried out in order to achieve that maximally unified guide to the development of mathematical concepts toward which our subject has always been striving.